Now that we have basic IPv6 internet connectivity, let's implement NAT64. We'll also make the appropriate DNS updates to provide the required connectivity within GlobalMantix. Let's start on R9, our new NAT64 router. I've connected it to R7 using a single Ethernet connection, then used VLANs to create two logical links. VLAN 4 is the IPv4 interface, and VLAN 6 is the IPv6 interface, which I hope is intuitive. Let's check out the IPv4 side first, which communicates with the internal GlobalMantix network. The interface is dead simple, with only an IPv4 address, no IPv6 address, and NAT64 enabled. With NAT64, you don't specify directions like in or out, since that doesn't really make sense in this context. Next, let's check out the VLAN 6 interface to get a clearer picture on how the two sides of NAT64 are configured. This interface is a bit more complex, as it contains a few IPv6 addresses such as LLA and ULA, along with suppressing RAs. NAT64 is also enabled as you'd expect. There are a few caveats though. First, the Cisco IOS NAT64 process does not work if the IPv6 next hop away from the router uses a link local address. This makes no sense to me and I can't justify it. That's the only reason I've configured ULA addressing here, and I left the mask as /64 just to keep things simple. In real life, you could mask down if you like. Second, I've disabled ICMP v6 unreachables to prevent denial of service attacks against the NAT64 router. If incoming traffic destined for the network-specific NAT64 prefix does not match the NAT64 access list, the router will send back some administratively prohibited unreachables. That's nice in a lab, but it's too much information to leak over the internet, so I suggest disabling them in real life. Next, let's check out the global NAT64 configuration. These three commands effectively govern how NAT64 operates. First, we specify a network-specific prefix of 2020:6464:/96. Remember, NAT64 often uses a /96 so that only the last 32 bits change, allowing for an IPv4 address to be appended at the end. Traffic arriving from the internet towards this prefix will be routed to the NAT64 router for translation, and we'll set those routes up shortly. We also need to define an IPv4 pool. This is used for the IPv4 source addresses when translating from IPv6 to IPv4. The IPv4 GlobalMantix hosts need to respond to something, and these virtual IPs represent IPv6 internet hosts through NAT64. Last, as with most NAT technologies, we specify an access list. Let's check out the ACL to see which traffic matches. The ACL has two entries. The first entry tells NAT64 not to translate any IPv6 packets sourced from 2020::/16, which is our own GUA prefix. It almost never makes sense to perform NAT64 on your own traffic, so we want to ensure that this never happens. Then, I recommend being very precise about which subnets are candidates for NAT64. In our case, we only want to provide access to our data center VLAN, not our core routers or client VLANs. I'm using a /120 to only wildcard the last 8 bits, covering all of VLAN 20 in the data center, but nothing else. Also, notice that the source of the traffic must be from the broader IPv6 GUA range of 2000::/3. I don't want ULA traffic or other internet bogons being translated accidentally. Now, let's talk routing. We could run OSPF v2 or BGP or whatever to connect this router to R7 on both IPv4 and IPv6. However, I personally prefer to use static routing on both interfaces. I prefer this because sometimes your NAT64 router isn't a router but is a beefy Linux box or some other contraption. Those devices may not have fancy routing protocol support, so I suggest keeping the integration simple. Let's quickly explore the static routes on R9. There are two IPv4 routes. One is for all the internal transit networks, giving R9 access to our NTP servers and various transit links for connectivity testing. The other is for all client VLANs, both end user and data center. Because R9 has routes for all of these VLANs, all we have to do is expand our NAT64 ACL if we want to provide translation support for those hosts without needing to modify any static routes. Last, there is a single IPv6 default route that directs all upstream traffic to R7. Remember, Cisco IOS NAT64 will not accept a link local next hop here, so I'm specifying R7's ULA address. Now, let's handle the routing on R7. I've displayed the static routes on R7 using the same command. I'll focus on the two that are relevant to NAT64. The IPv4 route to the 100.64.0.0/24 network specifies the NAT64 pool hosted on R9, which will be the source address for the translated packets. The rest of GlobalMantics needs to know how to reach this, so I've applied a route tag to make it easy to redistribute into OSPF v2. We also have an IPv6 route to the NAT64/96 prefix, also with a next hop of R9. Incoming IPv6 traffic from the internet destined for this prefix will be routed to R9 appropriately. In the future, when R7 has been fully dual stacked, non-NAT64 traffic will flow normally through the core network and avoid the NAT64 detour. For completeness, I want to show how the IPv4 route is redistributed into OSPF. We'll check the route maps and OSPF v2 configuration to show one implementation example. At the bottom, the route map simply matches tag 64, which was applied to our static route representing the NAT64 pool. Then, we redistribute that static route into OSPF v2 so that the rest of GlobalMantics can reach it. To prove that it worked, we can check the OSPF redistribution details using the command shown. Okay, we see the NAT64 pool redistributed properly, and I'm confident everything will work. You shouldn't trust me though. Let's verify it next.